Today we are going to start this topic of capacity of RC section subjected to combined axial flexural loading and axial load. Right? This is one of the important considerations that we are going to do for any member design. But how did we come to this one? Why did we choose this topic and what does it mean? Let's go a little bit back and then try to come back to this question. You remember this diagram last time that we said that we are going to talk about loads and actions and deformations, and we said that we don't want to do that one here. That is the job of Dr. Panchit for now. Our job is here. So now we are going to talk about this part: strain, stresses, stress resultants, and back to the capacity side. So we are going to talk about the capacity or the stress resultant. Okay, and that when we want to talk about that, then let's see what are we going to talk about. These two paths, you remember last time we talked about one like that, right? So we are going to talk about this side. We started with material response, we finished first lecture, now section response. So this is where we are. So keep this diagram in mind. We are gradually going from this diagram down. So we are talking about section response today. Just to remind you where we are. Okay, structures. I showed you this slide also last time. We have so many types of structures: shell structure, truss structure, this structure, post tension, pre-tension, solid, and so on. They're all made from different forms of structures. And then also you have the walls and flat slab and pipes and stairways, and so different ways of looking at the structure. That means structures are quite complex. They can have many forms. They can have many type of members. So how do we start this design or this understanding? Which structure are we going to pick first? Right? We cannot deal with them, all of them. So we are going to pick out of that one of them. Now this is the way structural engineering simplifies the problem to deal with. That is the structure, the real one, continuum. That means it's going in all directions with no form, no nothing. And then from that we can cut down a regular block. We can say, okay, that is too difficult for me to deal with. Why don't I take a smaller piece out of this one? And then take a regular body as a solid block to start with dimensions and form, clear dimensions and clear form. So if this is a solid block with 3 dimensions, then it is still difficult for us to deal with. It has many issues. We need to go further one more step. And when we go further one more step, we go 2 ways. In one direction we say, let's say this dimension is too small compared to other 2 dimensions, so we end up with this form, which is like a slab or a plate. So the definition of a slab or a plate is that one of the dimensions is too small compared to other 2 dimensions. What is too small? We don't know. Let's say too small for now. Then another we say no, 2 dimensions are too small compared to 1 dimension. Right? So these are the 2 possibilities. So we have 3 possibilities. All dimensions are of the same order. 1 dimension is too small compared to other 2, and 2 dimensions are too small compared to 1 dimension. So these are the 3 possibilities. So we divide our study into these 3 possibilities and say this is solids, this is membrane, plate, shell, and this is beam. We call it beam, but actually it's a 1D element. This is a 3D element, this is a 2D element. When we say 1D, that means we are only the length of the member is modeled or considered. Other things become a property of the cross section. Here, 2 dimensions are considered, 3rd dimension become a property. It is not actually considered. Which means no matter how thick this thing is, if it is a slab, we still design it using the same approach. Similarly, no matter how big this section is, if we call it a beam, we still design it using the same approach. And that creates a big problem. Because, let's say you're talking about a footing, pile cap, right? Let's say 4 meter by 4 meter by 3 meter. As big as this room. Now, can we call it a slab? No, but we call it, people design it as a slab. We design the footing as a slab. So that is obviously wrong, but that's how we do it because we have classified the footing to be a slab. So we design it as a slab, whether it is this thick, that thick, or that thick, we don't make any distinction. And that creates a problem that we are going to tackle, of course. Same is the case here. The beam, we are saying that beam is a beam, but what if the beam is 2 meter deep, which is quite possible, 4 meter long, and half meter wide, right? Now the behavior of that, although we call it a beam, and a beam which is only half meter by half meter, but it's 10 meter, is obviously not the same. But we treat them the same for now, right? And we are, of course, we are not going to treat them like this in this course, but normally we treat them like that. And that is the reason why we get this, I said too small, we don't know exactly the number here yet, right? So let's now first of all start with this member. Frame member, beam member, one line element, in which we say that 2 dimensions are too small compared to 1 dimension. How small? Don't worry about it for now. Okay? If you take that member, if you take that element, it could have any shape. So I don't want to draw a rectangle because it will give you a wrong impression that we only deal with rectangular shapes. The shape could be any, right? And it could have a length. This is the axis, it could have a length. If I cut a plane which is normal to the member axis, that becomes cross section. Cross section. So cross, we take the line, perpendicular to the line, we draw a plane, and whatever you get on that plane, that is the cross section of that member. So that cross section plane, so that means now we are talking about a plane, and then we forget about the rest of the member, we say, let's study this plane. And there could be many planes along the length, right? But let's take one plane at a time, and that will become our cross section. And at that cross section, we could have 7 things going on that cross section with respect to the plane and the line. First of all, there could be a movement of this point in this direction, ux. There could be movement of this point in this direction, uy. There could be movement of this point in this direction, uz. There could also be, about that axis x, there could be rotation of this cross section. There could be rotation of that cross section, so rx, ry, and rotation torsion about this one, rt, rz, right? And this thing, 3 arrows. What is that?
Torsion.
No, torsion is not. Torsion we already talked about. No. What is that, the 3 arrows? No. Warping. Have you ever heard about warping? No. So hear it. Warping is a 7th degree of freedom. We don't have 6 degrees of freedom. We have 7 degrees of freedom on a cross section. We have ux, uy, uz, rx, ry, rz, and wz. So what is warping? No idea. Warping is the twisting of this plane. Normally, for all of the other, the assumption is that the plane remains plane after deformation. Correct? That is what you have learned, that after deforming, the plane remains a plane. But warping says that no, the plane does not remain a plane, the plane also becomes distorted. So plane is no longer a plane after deformation, and that deformation of the cross section out of plane is called warping. Right? So please remember that warping is very important, and it needs to be considered or it needs to be ignored. And it's very interesting why civil engineers did not learn about this until now, even though it's present in every case. Yes, please, come in. So the reason we sometimes do not study warping is that either we can ignore it because the warping stiffness is too large, or we can ignore it because the warping stiffness is too small. Right? Now you will say, what kind of logic is that? Right? Yes. Concrete sections, they do not warp, so we can ignore them. Their sections actually remain plane. So their warping stiffness is so high that they do not warp, so we can ignore it, right? Steel open sections like high sections, they are so flexible that they warp a lot compared to the warping is so much that it just distorts the cross section but does not produce large stresses because the stiffness is too small. Because stiffness and stresses are related. If the stiffness is too small, large deformation, small stiffness, still no stresses. Understand the point? So we can ignore the warping in two extreme cases, but there are a lot of cases where warping is extremely important, and those cases are cold form steel. You know what's a cold form steel, right? Okay. Cold form steel is when you take a steel plate and you bend it into section, it's not solid. The entire design of the cold form steel is dependent on warping, and also steel section. In certain cases, when the ends are fixed, warping becomes important. When warping is restrained, then warping becomes important. So it's a complicated stuff. Sometimes we either allow the section to warp, so we can ignore it, or it is so large that it doesn't matter, or if we fix it and the warping is present, we have to consider it. Warping is, and look at the three arrows. The units of warping, so every one of them has one property associated with that. Axial deformation has which property of the cross section? Axial deformation? Cross section property. I'm not talking about compression. Which property governs the axial deformation? Which stiffness governs the axial deformation? Cross sectional area. People. Cross section area. If you have large area, you have large stiffness. Correct? AE over L. Correct? AE over L is the cross-sectional stiffness for axial deformation. So, for axial deformation, cross-sectional area, correct? For UX, which property of cross-section? Shear area in X direction. U by shear area in Y direction, which is not the same as cross-sectional area or the axial area. Different areas, okay? Even the cross-section has the same dimensions. Moment about Rx, moment of inertia about X, Ixx. Rotation about Y, moment of inertia about Y, Iyy. Torsion, J, torsional constant. And warping constant. Right? So we have 7 properties of the cross sections corresponding to 7 deformations. Axial stiffness, what is the unit of axial stiffness? Axial area? Area cross section, what is the unit? Inch square, unit square, right? Length square. What is the unit of the shear area? Same, right? Length square. What is the unit of the moment of inertia? Unit 4, length 4, alright? Torsion? Unit 4 is the same property. Torsional constant, unit 4, right? Warping constant. What unit is warping constant? Unit 6, right? So we are dealing with properties from area, unit square, length 4, and length 6. Of course, you never heard about warping constant, so you do not know what it is. Extremely difficult to calculate warping constant of cross sections. Very complicated equations to calculate the warping constant. Even the torsional constant J cannot be calculated reliably. Very complicated. In fact, if you had taken Professor Warsak's course in finite element, his first problem would be to write a finite element program to calculate the torsional constant of the beam, because the problem is so complex that you need finite element analysis to calculate that. So for a general cross section, it is very hard to calculate these properties. You are dealing with, I know you remember A into B is equal to area, and B D square BD cube over 12 is equal to moment of inertia. Yeah, please forget about all of them because they are only valid for very, very simple cases which will not work in our case. So we will need more comprehensive way of calculating these things, which we will talk about. I'm going to give you my book called Understanding Cross Sections next lecture, and that explains all of these things in detail with the formulas, equations, and stuff like that. Okay? So that book will go together with this course. Okay, I will put up that book next time. Okay. So most of this course is taken from that book actually, or the book is based on this course. Either way. Now these are the things that I was talking about. 6 items, 7 items, and 7 forces. Now each of the degree of freedom, as we call it, or each of the deformation has a corresponding force component that we need to deal with. Right? So we have 7 directions of movements, 7 properties, 7 displacements, 7 types of forces, and then corresponding stresses. Alright? So each direction, axial force and Z, we call it, because it's Z direction, Vx, Vy, 2 shear forces, Mx, My, 2 bending moments, and torsion, Tc. Right? Warping is actually related to torsion plus these axial forces, so we do not put it here. Actually, there is no force. We call it warping moment, but normally we don't talk about it because it's not external, it's internal generated because of the deformation of the cross section. So there is no warping force as such. It is a product of the torsion and axial force. Right? So warping, axial strain. So this gives you kind of a relationship between which deformation, which strain, which stress are produced and what forces are induced. So this is like a summary of a cross section. Right? Stresses, strains, displacements, forces, all related to each other. And what is finally happening? You have basically axial stresses, axial strains, and shear stresses and shear strains. Only 2 things left in the end: axial strain and shear strain. And axial stress and shear stress. Everything else disappears. So at the cross section level, finally we are left with axial strain and shear strain. So we are going to talk about first axial strain and all of the things related to axial strain, because I told you in the first diagram that I'm going to start from strain now. We're going to forget about everything else. Let's start with strain. So I pick axial strain, and if you look at axial strain, you can see axial strain is present in many places. Axial strain is here, axial strain is here. This one Rx, Ry. What is that? RZ? RZ, axial shear strain. No, this is wrong. This should be axial strain. There's a mistake here. Shear strain. This should be axial strain. So these 2 axial strains, and also we have axial strain here. So 3 components are related to axial strain: axial load and 2 moments.
You also have warping.
And warping also. Warping also axial strain, because I said so. Axial strain is present in 4 of these, and shear strain is present in also 4 of these, because it's common. Right? Shear is common in warping and bending, and that creates the interaction between shear and moment. Right? So we'll come to all of this gradually. So, but anyway, this is our starting point. Okay, cross section. Now, this is part of the strength of material and other courses. It's not really part of concrete, right? But our starting point is here. Let's now get down to our problem. Our problem is that there is a building here in which we may have columns, we may have beams, or we may have some braces, some other things. And they may have any cross section here: rectangular, circular, this one, general section, built-up section, composite section, steel section. All those kind of sections may be there. Steel inside concrete, concrete inside steel, concrete inside steel inside concrete, and all these combinations, right? Plus pre-stressing, post-tensioning as forces on top of that. So, and reinforcement anywhere. So we have a complex problem in the sense that we have so many types of cross sections, so many types of their combinations, and we have beams and columns to deal with. So now we are dealing with these cross sections and these problems. So traditionally, until now, if you look at any books that you read, they will teach you how to calculate the capacity of a beam and design a beam, how to design a rectangular beam, how to design a T-beam, how to design a beam for singly reinforced beam, doubly reinforced beam. You have all read that about that. How to design an L and how to design a column, circular column, rectangular column. Correct or not correct? So for every type of member and every type of section and material, they will give you different procedures to design, different way to handle it. And steel section will be different, composite will be another book, another chapter, another code, right? But in this course, we will see that all of that is completely unnecessary. We just only need one equation to handle all of this, what you see in the board. Doesn't matter what type of member we have, doesn't matter what shape we have, doesn't matter what material we have, doesn't matter what combination of materials we have. We only need one equation to handle the capacity of this entire cross-section problem. It doesn't even have to be concrete. It could be fiber, it could be carbon fiber, it could be bamboo, or it could be silk fiber. It doesn't matter what is the material it is made from. You only need one equation, one procedure to calculate the capacity issue as far as this is concerned. All right? So that is our objective, to develop that equation now. So it is possible to develop a single theory for determining the axial flexural stress resultants of most types of concrete members for all design methods and for most design codes. Not only we are going to integrate the cross sections and types, we are also going to integrate various design methods and various design codes. So that means ultimately the codes and design method will also become irrelevant once we are done with this one. So only one equation should be enough to do all of that. And then unifying beams and columns, unifying reinforced and pre-stressed concrete, unifying working stress and ultimate strength, unifying different cross-section types, circular, rectangular and all, and incorporating various stress strain models, right? All of that we will do because this is code dependent, so we will put them all together. So let's now start to do that step by step, one at a time. First of all, beam and column. What is the difference between beam and a column? What is a beam and what is a column? How do you understand?
Beam is fragile and the column is the compression.
The basic definition is absolutely wrong, right? Because column is an axial flexural member. It has both bending moment and axial force.
So dominant forces are
not necessarily. Moment can be dominant in a column, in a small low-rise building. You have absolutely no idea, or you cannot define it at all. Same as the case with the beam. We say beam is a primarily flexural member, but beam in a typical reinforced concrete building, where we have earthquake forces, it also carries a lot of axial forces. And then what if the beam is not, if not the member is horizontal? You say this is column, this is beam. What about this? What do you call this? Is it a beam or a column? Tell me, how will you design that? Correct. So we don't need to worry about whether it's a beam or a column at all. It's just a member which is subjected to any of these forces, to bending moment and axial force. If it's a beam, no moment, no axial force, put it 0. Why do you have to say this is a beam? Let's say it's a member subjected to one axial load and 2 moments. If it is a column and there is no moment, okay, just put them 0. Don't need to define any theory for that. All you need is the same equation, just the ability to put some things at 0 or very small. So then we don't have to worry what is the limit, right? Normally the SCI code says that if the axial force is less than 10% of the axial capacity, you can consider it as a beam, correct? But you still have to calculate the axial capacity. Once you already calculate it, why do you need to ignore it? You already done all the job. So what's the problem there? So my point is that we don't need to worry about this one. Normally we say that the beams are rectangular, T, L or box. And column can be circular, polygon, general shape or anything. But obviously if it's a polygon, then rectangle is also a polygon, right? L is also a polygon. So basically we are dealing with a polygon cross section of a column. Then beam is already covered, correct? So we can unify beams and columns and stop thinking about beams and column as two separate things by considering a column with a general section. Correct? No question about that? Sorry. Okay. Next one is unreinforced, reinforced, partially pre-stressed and fully pre-stressed concrete. You have both separate courses on pre-stressed concrete, separate books on reinforced concrete. But what is the difference? Unreinforced concrete, there is no reinforcement, there is no pre-stressing. Reinforced concrete, there is pre-stress, there is reinforcement, no pre-stressing. In a partially pre-stressed concrete, we have some reinforcement, some pre-stressing. And for a fully pre-stressed concrete, we have no reinforcement, only pre-stressing. So what is obvious from this table? We just consider a partially pre-stressed section and all the others are already included. Just set whatever is 0 to be 0. You don't need a separate book or a separate course for that. Correct? So we pick this one, and if it is an unreinforced section, we will simply put them as to be 0. If it is a reinforced, we will put this to be 0, and so on. So we don't have to draw a line. It is the same thing that we can do. So that means we are saying that let's talk about a column which is partially pre-stressed. Then we cover everything. Correct? So this is what we consider. What happened? Material models. What do you see common in all of these material models that we saw so many on the other day? What is common? What is common is that they are all made from a series of points connected by a line or a curve or a segment, correct? So this curve, there is no difference between this curve and this curve. This is made up of 1, 2, 3, 4 points which happen to be straight segments. This is made up of an n number of points which are on a curve, right? So if I define my stress strain curve as a series of points and don't worry about the shape, I'm done. I can consider any stress strain curve with that. After I just simply have to specify the coordinates of the point in a certain way, and I can include every stress strain curve in my theory, because I'm going to develop the theory based on a series of points which define a curve, which define a relationship between stress and strain. So this curve, this curve, this curve, this curve, they all become same to me, because I don't need to see the curve shape. I just need to know that these are a series of points which are connected by small straight segments. And if I can develop my theory based on that assumption, then later you can define whatever curve you have and it will work. Correct? So that means now we can combine all of the different codes, PCA, PS, and Whitney, and Mender, and non-Mender, everything into a single formulation. We don't need to worry about what concrete curve we have to use, because it's just a curve. Same for the steel. Right? Now, what is the difference between concrete and steel? Material, or fiber, or carbon fiber, or plastic, or any material. How do you differentiate between two materials? Tell me, what makes two materials different? This curve and concrete curve, they are different, right? That's the only difference, that they have different curves. You cannot tell me that reinforced concrete and steel, anything else other than the curve is different. This has a tension and a compression similar. Concrete has no tension side, which we have decided to ignore. Actually, it's there. Tension also is there. But the point being that why is this curve different from the previous one? This is also a series of points. The previous one also was a series of points. So basically the program or our theory or our formulation does not need to know what material it is. It only needs to know what is the stress strain curve. It could be plastic, it could be glass, it could be whatever you need, right? So basically what we are saying is that if you develop our equation in such a way that it only relies on a general polygon cross section, having a material assigned to it with a certain connected points, we are done. We do not need, same can be then applied for concrete, steel, aluminium, bamboo, banana, whatever you want to model. You agree with that or not? Right? So it's as simple as that. We do not need all of those different way of creating this problem. It's just a simple problem of a cross section with a certain material, with a certain stress strain curve, and that's it. Other than that, nothing. Correct? Okay. So, what is the difference between various limit states? Let's come to that now. Various limit states simply use a different level of stress or strain on the stress strain curve. That is all they are. They limit the stress or strain value for a certain purpose on the stress strain curve. They are still on the stress strain curve or the load deformation curve. To control cracking, they say don't put crack width. Everything is controlled, so you are within a certain strain. So basically, it's a control on strain on a stress strain curve, which means we don't really worry about that because you can give us any limit on the stress strain curve, and we can calculate the corresponding capacity for that level. Because this curve is there, right? You can calculate stress for any strain level. If you say strain is very small, fine. The curve, I can calculate the corresponding stress from there. If you say strain is very large, I can still calculate because I have the curve. So basically what we need is, we need a cross-section shape defined by a polygon, which is a series of lines, and a curve which is also a polygon or a polyline defined by a series of small lines. With this information, we can actually solve the entire problem of this flexure axial thing for every possible combination that you can think of. If you all agree on this one, then we can move ahead. So now if you ask me a book that gives you all of that, maybe there is any book which will give you this information in the way that we are dealing with, right? And then later we go back to special theory. So based on this idea, we can unify everything. Now I'm not just talking about this just like this. This is the procedure that we have implemented in most of the computer programs that all the engineers use around the world, including CSI section or CSI call. So many programs have been developed using this formulation of this theory, right? So it's actually, that works in reality because then you can use it in a general manner, okay? So what is the general procedure then? After having all done that, the procedure is very, very simple. Assume a strain profile. Assume that the cross-section is deforming in some way. It doesn't matter what way. It is deformed to some level. So we have a strain on the cross-section. Corresponding to that strain, we will go to the stress-strain curve of that material and calculate the stress. Easy, correct? At every point, we can calculate the stress. And then we simply add up all the stresses to get the force, and that's it. We got the capacity. And this capacity, we can compare with applied forces to calculate whatever vector of safety you want to put or you don't want to put. That's it. Correct? So it's extremely simple concept. And assume specific depth of neutral axis, assume maximum strain, and determine stresses. So these are things I will show one by one. This is exactly what you have been doing before, but you have been doing it without knowing that what you're doing is actually very general and can be expanded to cover all of the other cases also that you do not consider, right? Determine the strain in each component and the corresponding stress-strain relationship, calculate stress resultant for each component, calculate the total stress resultant. Right? So we will go to these steps one more time. But basically the idea is very simple. Strain, any strain profile, from strain calculate stress, from stress calculate the force. And that's If you calculate all the stress, all the axial stress, sum it up, it will become axial force. If you calculate the moment of that stress about any axis, you get the moment. Correct? So both moment and axial force can be done, and moment can be calculated about any axis. So biaxial bending is also done, right? Not only uniaxial bending, but biaxial bending also done at the same time. So you can use this concept for designing of beams and columns, both for axial, uniaxial bending and biaxial bending, right? This is the cross section that we are going to deal with now. Please look at this shape and let's spend some time on this to understand what's going on here, because now things get a little bit more complicated than what I was saying. It will sound very good on that slide, looks too simple. Obviously it's not. If it was too simple, you would have known it, right? So why is it complicated? We will see step by step. First of all, let's consider a cross section of any shape which has a steel shape, concrete with steel inside, with rebars, and also a pre-stressing strand. Obviously, this may not be a real cross section, doesn't matter. But we're just saying that there's a cross section which has many materials: a steel section, a pre-stressing, a reinforcement, and concrete. It's a cross section, right? And we say that this is the normal direction of the horizontal, any arbitrary axis, right? But the cross section is bending about an axis which is inclined at an angle theta. That means normally if you take a beam, it will be bending about this axis, right? We assume that the beam's cross section bend about the horizontal axis, which is perpendicular to the direction of the bending. Let's say that this is an inclined member somewhere, and it is bending on the direction, the sideways, due to any loading. That means it's not bending, so it is like this one, rotated, and also it's bending about an axis which is at an angle theta. Correct? So far clear? Then we say, okay, this line, let's say this is our neutral axis somewhere here, this dotted line. What is a neutral axis? We will talk about that. In fact, there is no such thing as neutral axis, but okay, let's see that there is a neutral axis, right? And we say neutral axis is here, and based on that neutral axis, there is going to be a strain. So there is going to be some strain here, compression strain and tension strain, correct? So this is the strain diagram of the cross section, assumed, correct? Any strain, it is bending. We don't know the strain, doesn't matter. All we're saying is there is a strain. And the diagram, and for now let's assume that the strain is plane section remain plane for now. Okay? And based on that strain, we can calculate strain at every level. So based on this strain, this is the stress strain curve for concrete that we've seen already. So we take that stress strain curve and plot it here, corresponding to strain. Because zero strain here, this is the same curve that we saw, just plot it like that. Correct? So the stress strain curve of concrete comes here. The stress strain curve of steel section comes here, whatever that is, right? It was linear, bilinear, okay? It comes here, it should. And then for each bar corresponding to the strain, we can calculate the corresponding force anyway, because we know the strain at that location. So now we have a situation in which we have a cross section bending about an angle with a neutral axis like this, strain like this, stress strain is given. This is the center of that stress. We can calculate. Now I can add this stress on this area, calculate total compression. I can add all of these forces in this bar, and I can add the total stress in this location multiplied by the area of that thing over there, and I can calculate the total stress resultants. Not stresses. Of course, stresses are there. Stress resultant, sum of the stresses. Stress resultant is what we want, sum of the stresses. We are not interested in individual stress. We are interested in the total stress, sum of the stresses on the cross section. Because if you put a force P, what do you get? You get a P divided by area is a stress. So stress multiplied by area is equal to P, right? So we want to do the reverse because last time I told you we are taking from strain going this way. So we want to go from strain to stress to forces. Correct? So which means that now based on this assumption we can get the stress resultants from the section. As long as we know two things. And what are those two things? We know the angle of the bending and the depth of the neutral axis and the strain profile. Right? Basically, if we know the strain profile and the angle at which the strain profile is there, we can calculate the stress resultants. So please, if you do not understand, I will explain this figure as long as it takes for everyone to understand, because this is the basis of the rest of the theory. If we understand this, then we will go ahead. Finally, we will get this equation for that cross section. Okay? Don't worry how we got it. We will get there. Let me complete the discussion. So this equation is saying that there could be n number of materials in the cross section with n number of bar types, n number of shapes, and what we need is basically the stress at each location at xy point multiplied by the area of that small location, integrate that over the area to get the total stress. I need to explain many things here, sorry that I skipped 5-6 slides. And you get this one. This component is coming from the bar type of cross-section components, but this could be 1 plus 1 plus 1, there is a limit, it can go on. Moment. And these are the gamma factors coming from material gamma factors that we talked about from the code. These are material factors. These are the capacity reduction factor from ACI code coming from the capacity for axial and flexure. I mean, I have to explain all of these things. But basically, ultimately, this equation will solve the problem for British, ACI, Canadian, Norwegian, whatever code you may have, whatever material you may have, pre-stressed, non-pre-stressed, concrete, any material, any configuration, anything. So this basically, these three equations are enough to determine the cross-section capacity of any thing that you can think of. That is the bottom line, right? Including the factor of safeties, including the capacity factors that you may want to include, both material-based and action-based. All right? So next time we spend time in between, because then I'm going to give you another assignment, not today, next time, based on the fibers. When we talk about the fiber discussion, we will come back to this equation. Basically, you can see that I already have this comparison. This is the simple case of this that I was trying to draw before for you, of a beam that you have studied. Beam cross section, 2 bars, and this one, this one, this one, and that is the equation for the moment, correct? And this is that case, and these are the equations. Both of them are in concept exactly the same. There is no difference between them. This is also taking the area of the bars plus the area of the concrete, adding them together to get the total moment multiplied by the lever arm. This is also doing the same thing, multiplying by the lever arm, force multiplied by lever arm, force multiplied by lever arm, and so on, and adding them all together. It is just doing it in a more general, comprehensive manner. So basically, both equations are doing the same thing. And this is a special case of this. Just remember that. And this is the general case that will solve all of the things that I showed you earlier. This will, of course, only solve this problem. If you change that to another, it will not solve it.
So it means if you put the values of these parameters in that equation, satisfy it.
It will satisfy. Absolutely. Absolutely. This integration is actually summation of this block here, B into A. So if you convert that into that, it will become the same thing. Integration, normally we cannot do integration. We do numerical integration. Now, you know that in computers we can't do integration, right? We do numerical integration. So numerical integration is we divide the things into small portions and add them up together. So this integration will actually become a summation later when we implement it. right? So with that equation, we can solve now the section, cross-section response. Now we can see a lot of things with that equation. And neutral axis, ultimate stress, tag section stresses, section capacity, moment curvature curve, elastic stresses. So many things can be determined from that. So this is the governing equation that we have talked about, and this is the result of that equation. I'm going to, don't worry, this lecture will be repeated with some more details. I just want to give you an overview first. This equation can be plotted like that. That the outcome of this equation is that surface, what you see over there. So we will say, how can we get that surface from this equation? Now, remember, this equation is valid for one angle theta and one depth of neutral axis, whatever it is. Only valid for one angle and one depth. As soon as you change neutral axis depth, you have to re-evaluate everything. And as soon as you change the angle a little bit, you have to re-evaluate everything. So if I calculate all the points by using all of the possible thetas from 0 to 360 and all of the possible values of the strain, I get this surface. So each point, because this will give me one combination of n, m1, and mx, and I'll get one point here. If I change the angle a little bit, I will get another point here. If I change the angle, I will get another point here. If I change the neutral axis, I will get another point here. So this vertically will give me the change in the neutral axis depth, and horizontally the points will give me the theta angle. So if I keep the theta constant and change all of the neutral axis depth from 0 to this one, I will get one line here. And then I change the angle and repeat the same, I will get another line here. So I will get a surface. So I can generate a full surface from that equation by changing the neutral axis depth and changing the neutral axis angle. Because this equation is useless for design. Even though this equation is beautiful, it's useless. Why is it useless? Because if you have a moment, let's say 100 ton meter or 100 something kilonewton meter, and axial force, let's say 200 kilonewton, and you tell me how much reinforcement I need in a cross section, this equation cannot tell you anything. All it can tell you is that if you already know the reinforcement and you already know the section and you already know everything, it will just tell you what the capacity is. So it's very nice but useless in itself, because it does not help you to design anything. It only tells you what the capacity will be if you provide a certain amount of reinforcement and section. So everything must be known before this equation can be used. But in design, we don't know that. Right? We want to calculate the reinforcement. So that equation has no meaning to the designers, because they want to know the amount of reinforcement and the section size and the material strength. Then we divide the work between two people. People who work on the computation side and the engineers who use the computations. Okay? So the computation side will say, okay, I understand your problem. What I'm going to do is I'm going to generate this surface for you. For all possible combinations of the neutral axis rotation, and then this becomes the failure surface for your cross section. So any combination of mx, my, and z which is inside is acceptable, and any combination which is outside is not acceptable, because that means the strain limits or whatever you set will be violated. So that becomes a failure controlling surface for that section. But still doesn't help me, because the reinforcement must be known before the surface can be generated. Right? So the next step is, we generate many surfaces for different reinforcement ratios or different and then quickly find which one we need. So I mean, it's a computational problem, but ultimately we use this equation for design. I will come back to this in more detail. Right now, just continue and give you the overall picture. So you get this nice looking shape. We call it moment interaction curve, or moment interaction diagram. And what are these blue lines? I just put some planes to tell you that these are the planes, vertical plane and horizontal plane. You can cut this diagram for many uses, right? Are we understanding so far? Forget about how the equation is derived, right? We'll come to that. But now I'm saying the application of the equation. How can we use that equation? The use of the equation is that we generate this surface, this nice 3D diagram from that equation. This is a plot of that equation by changing the angle of the cross-section's deformation and the neutral axis depth. So each angle from top to bottom, we change the neutral axis. For each, then rotate it again, do that again. Rotate it again, do that again. We do it many times and we get this surface, right? And this surface shape will depend on the cross-section shape. It will not always be like this. Cross-section shape will govern the shape of this. It could be a perfect, nice melon, or it could be a guava, or it could be a very strange fruit shape, right? Depending upon the cross-section that you use to generate it. But they all look like fruit somehow, ultimately. And this curve here depends on the 4 factors. If you remove those factors, this will become different. So everything is embedded in this diagram. The capacity factor will affect this one, the reinforcement location. If you distribute the reinforcement unevenly, this shape will no longer be symmetrical. If the cross-section is perfectly symmetrical, this shape will be symmetrical. If it is not, the cross-section is not symmetrical, the shape will not be symmetrical. So this is a property of the cross-section. Once the cross-section is known, the surface is known. So normally in the programs, in the design programs, what they do is, for the cross-section, if you have one cross-section, they calculate this one and keep it. And then after that, for all the loading, you can just check, is okay or not okay, or something like that. It can interpolate. So other things can be done. So we'll come to that, don't worry about it. So this is taken from a program called CSI Call, which we developed here. Now, other things. Let's talk about other properties, other behavior of the cross-section. That is just one of the things that we're talking about. This is the cross-section that we were talking about. And if you apply a bending moment on the cross-section with the axial load, let's say if the moment is 0, the axial load will be in the center. So this thing will be in the center, which is representing the point of application of the load. If you apply moment, it will shift to this direction. If you apply more moment, this here it will shift there. So the distance of this from the axis depends on the moment. That means eccentricity of the load depends on the moment and load, right? So m divided by p gives you eccentricity. So the location, you can visualize that as the moment comes, basically the point of application of load is shifting around the cross section. And because of that shift, you can imagine the cross-section will deform perpendicular to this point. So if this point is here, the cross-section will deform like this. So it will move this way, this side will come up, this side will go down. There will be compression here, tension on that side. Correct? So that means this point, this load gives you the idea that if you move around, the cross-section will keep on doing like this, right? Depending upon where the load is moving. So every time the moment is changing, the cross-section will bend to conform to that location of the load, right? And normally, in a typical building, if you have earthquake, wind and so on, the moment keeps changing depending on the load time. So that means for the same cross section, there will be many combinations of deformed shapes that will exist, not just one, right? Earthquake this way, load is here. Earthquake this way, it will shift here. Right? Earthquake that way, it will shift here, and so on. Depending on the moment direction, this load will keep shifting. So that means there could be many locations, and that this will govern the strain profile. Right? Because when it goes down, it will lift up the cross section in this direction, and it will press the cross section this direction, so the strain profile, and it will, there will be a line perpendicular to this somewhere here about which the cross section will rotate or deform. And that normally we call neutral axis, right? But we will learn later that that is not really the case. So, based on that, you can see the stresses will change, the stresses will vary from one direction to the other. So if you have load point here, there will be more stress here, less stress here, tension here, compression here. So you can calculate the elastic stresses on the cross section based on same approach both ways. So in one way we can calculate the stresses, and the other way we can assume the strain and calculate the stresses from this direction. And one is if we know the moment and know the load, we can calculate the stresses from the cross section. So two things are totally independent and not the same. Please remember this. From actual load, you can calculate the stress and you can calculate the strain, which will not be the same as the strain that you assume and you calculate the stress and calculate the load. So one way, I've shown you both paths, right? One path is apply the load, it will create the stress and it will create the strain. These are always called elastic stresses and elastic strains, right? And they are only valid if the cross section is deforming linear elastically, correct? If the cross section is non-linear, which we know is non-linear, that will not be true. Because why not? Because let's say you apply a load moment here, so load is acting in this location, right? And you get a strain of 0.002 or 0.02, for example 0.02. Now according to the elastic rule, you can calculate the corresponding stress. 0.02 multiplied by modulus of elasticity, you get the stress. But if that stress may be not matching with the stress strain curve that we have, so that stress has no meaning, correct? Because the cross section limit is 0.003, but your stress, you are calculating a strain which is 0.02, which cannot exist. So the elastic stress calculation based on the loading alone is not reliable, has no meaning to us, because it does not consider the material behavior, which may not support that stress strain value. That is why we don't do that. That is why we go the other way. But steel is more or less following a certain elastic system. So for the steel, more or less we can estimate before it starts to yield, right? So for steel, it may be okay within a certain range. For concrete, it is never okay to try to calculate the stresses this way. This is what it shows you. It is not taken from that program with diagrams. So it shows you that if you put the load here, it will lift up like that, it will go tension here, tension here, compression here, and this becomes your deformed plane, that is your original plane, right? And they are intersecting here. That is your neutral axis, as we call it. So neutral axis is basically the intersection between the undeformed plane and the deformed plane. So when you put the load here, it will shift like this, neutral axis will become like this. If you put more load here, neutral axis will shift this way. If you put less load here, neutral axis will become upwards, right? Which means the depth of the neutral axis is controlled by the eccentricity of the load. Correct? And of course the value, obviously. What is the neutral axis depth for zero moment? What is the depth of the neutral axis or the location of the neutral axis when we have zero moment? This is the depth of the neutral axis. We normally measure the depth from here. The distance from this point to this point is called the depth of the neutral axis. The depth of the neutral axis for zero moment is infinity. There is no neutral axis. The neutral axis does not exist when you have no moment. Neutral axis only exists when you have moment and axial load. What if there is only moment and no axial load? In that case, it will be 0. It can be 0, depending on the moment value, right? So those, sorry,
Neutral axis depends on moment and axis load.
both of them, right? Both of them have to be there. That is why when we're dealing with beams, when there is no axial load, the neutral axis depth is defined by only the moment value. It can exist over there, and the two forces are self-balancing. So the net P is 0, always. The compression and tension must balance, and must be equal to 0. And that is only existing, why? Because we force the strain to be certain value, which is not true. We always assume, no matter how small or how big moment is, that strain in concrete will be 0.003. Okay? How wrong is that? Because the moment may be very, very small and that strain may never be produced. But just for our convenience, we assume the strain to be equal to 0.003 always, irrespective of the moment value. Correct? So that condition of 0.003 strain never ever happens. Never ever happens. But still, that is the basis of our design in the codes. This is the depth of neutral axis I was talking to you about, that if you put the load somewhere, the location, the depth of the line of intersection between the planes and the farthest point in compression is the depth of neutral axis that we deal with. And that is how it will look like. The deformed plane and the original plane, they cut here, and that becomes your neutral axis. Right? Now, just to tell you, the deformed, this one is not a plane. We are just assuming it to be plane section. We have warping, or you can forget about that. Which means this cross section, this dark gray line is not actually a plane. It could be a surface all deformed and curved, which we do not know. That means the intersection of that may be a curve, not a straight line here. It could be intersecting. It is even possible that this thing is going up and down, so you have two intersections on the cross section. So you have two neutral axes or more. So the concept of a neutral axis is a convenient one in a certain case only when we assume the plane sections to remain plane and they intersect the cross section only one time. But in reality, these deformed sections are warped and could be anything, and they may intersect the cross section more than once, like in deep beams. We will talk about that later. Alright? But our theory still holds. Whether it is a deformed plane, if it's a plane or not a plane, we don't care, because all we want is, we want a strain at some location and we calculate the corresponding stress at that location and we continue. So if somebody can tell me what is the profile of the strain, it's okay with me. I can calculate the stress from that profile and I can continue. So our theory, our equation is not affected by any of those assumptions. It does not assume plane sections remain plane. It does not even assume perfect bond between concrete and steel, because each material can have its own stress-strain relationship offset by something. So slippage or the bond slip between concrete and steel can be incorporated into that equation by considering different strain for steel and concrete at the same level. So we can assume that the steel has more strain than concrete because it's slipping, and still our equations will be fine. Right? So they are quite comprehensive, quite complete, do not need any assumption at all. Right? So ultimate stress block, this is an interesting idea. ACI, coming back now. They assume that the entire portion which is in compression has a uniform stress. You've seen the stress strain block in concrete, right? Block. So they assume that everything between the neutral axis, B distance, beta distance away from that, and this one has a uniform stress on the concrete, just for the sake of calculation ease. That's all. It has no. The logic behind that is that that equivalent block has the same force as a real stress strain curve, right? So they simplify it. So it will look like that. In 3D, a stress profile for concrete weekly block will look like that. So the compression force will be equal to all of the stress in this area multiplied by all of the area under stress. Volume of this block will be equal to the compressive force, correct? So if this is not, so now because it is flat, so it's easy for me to calculate that area multiplied by this height, and I can calculate the total. But if this was a curve, then I will be in big trouble, because then I cannot calculate easily the force component. I have to now really integrate that stress over that area, and that is difficult, because this surface is actually going to be like this, because there's a stress strain curve. This is not flat. We have seen, depending upon the type of the curve, the shape of this thing will match with the stress strain curve. This is actually the stress strain curve, correct? So that means if there's a curve here, we have a surface of stress over the cross section, and then to calculate the integration of that on a complex cross section is very, very hard, and that is why those equations are not so friendly and for hand calculation. But in computers, yes, we can do that, right? In fact, in the end of this course, you will write by yourself a program to calculate the capacity of a general cross section using this fiber concept for Plumlee work. You should be able to write a general program, even in Excel, to be able to do this. All right? So we will divide it step by step. So that's how the stress will work in that way. Rebar stresses. Stresses in rebar vary by the distance from the neutral axis, as you can imagine, right? So different rebar will have different stress, and they may look like that. Some in tension, some in compression. So this we have to visualize what is happening to the cross section. Some bars have high stress in compression, some bars have low stress, and then after some time they will become equal. That is yielding. If the bars are yielding, then the stress will not change anymore. They will all be the same. So you can see that this way and this way, you can have this stress values in the bars, and after some point they become flat because of the yielding by linear curve. So now you may imagine that basically it's the stress strain curve which is governing all of that behavior. And if we know the stress strain curve, then everything else can just follow from there. All right? Two more slides or one more slide and we will stop. What is that next slide? Oh no, this is the complicated problem. Okay, we'll talk about it next time. Okay, let's stop here.